So, a very good morning to everyone. Department of Chemistry, Biochemistry and Forensic Science, MET School of Applied Sciences, MET University, Haryana, is proud to present a two-day international workshop on instrumentation techniques in collaboration with Faculty of Mathematics and Natural Sciences, University of Bengkulu, Indonesia, and with our very own Jamia Millia Islamia. Among other collaborative initiatives between AUH and University of Bengkulu under MOU, this workshop is an important professional activity to strengthen their partnership. The workshop will give valuable exposure to the participants who aim to carry out experimental research using UV visible spectroscopy and flash chromatography. May I now request Director, MET School of Applied Sciences, MET University, Haryana, Professor A.K. Yadav, to please unmute himself and deliver the welcome address.
Thank you, Dr. Anurag. It's a great morning, a great beginning of the new year. We are starting with a wonderful event, which is this international workshop on instrumentation techniques. We ended the last year with an international symposium to celebrate our Mathematics Day on 22nd December. And today we are beginning a new year with such a wonderful event, which is a collaborative effort between Amity University, Haryana and University of Bengkulu, Indonesia. All this has been possible because of the extraordinary efforts and initiative taken by Dr. Sal Prema Yudha from Indonesia and from Dr. Monica Watts from Amity University, Haryana. This kind of initiative, we can easily say that will take us a long way to further our research efforts. And we are also fortunate to have another collaborator, Jamia Millia Islamia University, who are actively involved in collaborating with our faculty members and researchers. This kind of initiative is one of the several initiatives that we undertake in Amity University, Haryana. And we are proud to have partnership with the University of Bengkulu, Indonesia. This particular workshop is going to be extremely beneficial to all the participants of Amity University as well as the University of Bengkulu and other participants who are attending this workshop. In fact, the importance can easily be gauged by the fact that we have integrated this particular instrumentation technique section as a part of our curriculum of master's degree in chemistry, forensic science and biochemistry. So I'm sure that after the sessions, the students and the other participants will immensely benefit from various technical sessions, which include lectures and the practical demonstrations. At this point, I would like to extend a warm welcome and heartiest greetings to Dr. Sal Prema Yudha from Indonesia, one of the resource persons and experts, eminent experts, who will be delivering sessions in this workshop. And also, I would like to extend a warm welcome to our Dr. Muhammad Abed from Jamia Millia Islamia, who will be another eminent expert who will be delivering sessions in this workshop. So on this occasion, we would like to thank our founding fathers, Honorable Founder President Dr. Ashok Chauhan and Honorable Chancellor Dr. Asim Chauhan, who has always inspired us to do things for academic excellence. Also, I would like to acknowledge the motivation and the support that we get from our leadership team at Amity University, Haryana, led by Honorable Vice Chancellor Professor P.V. Sharma and Honorable Pro Vice Chancellor Professor Padma Kali Banerjee, who have always supported this kind of events and this kind of initiatives, which are always aimed at academic excellence. We are always working towards giving our best to our students. That is what is our commitment. And I would like to extend compliments to the organizing team led by Dr. Seema Pathak and other members of the Department of Chemistry, Biochemistry, and Forensic Science. Also, there are student volunteers who have been associated with this kind of event. Uh, Particularly this event, we have roped in some students in order to inculcate organizational skills in them, and they have done admirably good job. So this is a great occasion to get going for a wonderful event, an excellent workshop, which is going to be very, very useful, not just for the future research career of our students, but also those who would like to go into industry. Their chances of employability will be greatly enhanced. So they will carry an additional skill with them, and they will be an asset to the organization, whatever they work for. So I look forward to a very, very productive workshop, a 2-day workshop with very useful sessions. And I'm sure at the end of the workshop, we are going to conduct an assessment for our students, as well as we will take feedback. So all the participants will be given an opportunity to give feedback, so that we learn from our experiences and we try to improve upon these experiences in the future events. So with this, I once again extend a warm welcome to all our guests, all the speakers, all the members of the organizing committee, and all the dear participants from various corners of the world. So thank you so much.
Thank you, sir. Honorable Vice Chancellor, AUH Professor P.B. Sharma, Honorable Pro Vice Chancellor, AUH Professor Padmakali Banerjee, and Professor Jarulis, Dean of Faculty of Mathematics and Natural Sciences, University of Bengkulu, Indonesia, could not join us due to some unforeseen circumstances. They have conveyed their best wishes for the successful organization of the workshop. Before starting the session, let me give a brief introduction to our first panelist, Dr. Sal Prema-Yudha, who will deliver a tutorial session followed by a demonstration of UV visible spectroscopy. Currently, he is a professor in Department of Chemistry, University of Bengkulu, Indonesia. He holds multiple research grants as PI from the Ministry of Research, Technology and Higher Education and Directorate General for Higher Education, Jakarta. He is a recipient of DART research grants for visits to University of Regensburg, Germany, and visiting scientist under the invitation for research in Japan from JSPS, Division of Molecular Nanosciences, Okazaki, Japan. He was also awarded a grant for a joint workshop on portable X-ray analytical instruments in Italy. He is an expert in handling NMR spectrometer, GC mass spectrometer, IR spectrophotometer, UV visible spectroscopy, among others, and has published more than 30 research papers in high impact factor journals. I request Dr. Sal Prema-Yudha to please unmute himself and conduct the tutorial session followed by demonstration. Well, any question can be posted in the chat box, and I shall be very happy to present them before the panelist. Over to Dr. Yudha.
Dr. Sal Prema, I extend a warm welcome to you. Especially, it is always a great pleasure to see you and interact with you, and I greatly admire your leadership and the initiative that you take to further this partnership between two universities. So we value your association tremendously, and we are grateful that you always are eager to spare your valuable time to these kind of useful events for students and researchers on both sides. Thank you very much.
Sorry for interruption, Anurag sir and Yadav sir. Dr. Juralis from Indonesia has joined, Dean of the department. So.
Oh, I extend a warm welcome to the Dean. Dr. Jaroles, it's a great pleasure to see you live. We can see you now on camera, and what a great occasion to have you with us on this great event, that is the workshop jointly organized by Amity University and University of Bengkulu. So we are very grateful to you to give your support and motivation for furthering this partnership between the two institutions. So thank you so much.
I request Professor Jarulis to please unmute himself and address the gathering.
Okay, thank you. Good afternoon for everyone. The Honorable Professor Eki Yadav, Professor Eshar Patak, Professor Dr. Padma Kali Banerjee, Dr. Saltrim Yuda, our colleague guys, and then Dr. Muhammad Abid from Jamia Mila Islamia, and all participants in this webinar. I'm very happy to be attending this webinar, and thanks to Amity University for inviting me in this webinar. As we know that Amity University, Haryana, India, and University of Bengkulu, especially for our faculty, signed MOU in the year 2020 and 20. Our institution very happy to this collaboration, and we hope our institution can be grow significantly to increase our quality. And I hope this workshop will give valuable exposure to the participants who aim to carry out experimental research as our topic this webinar. And also it will be helpful to graduate, postgraduate, and doctoral students in two institutions. And just that that I want to talk this meeting, and finally, hopefully, this cooperation or this collaboration between two institutions will continue in the future well. Thank you, Professor Aka Yadav.
Thank you, Dr. Jarulis. We greatly appreciate your thoughts and push to this collaboration between two universities. Thank you.
Yes, thank you.
Over to Dr. Sal Pramayutha.
Yeah. Okay, thank you, Dr. And then thank you, Professor Yadav. Okay, thank you very much for this moment. Then this is the second time we have collaboration in workshop for instrumentation, and today I would like to talk about the same topic with the last year, UV fish spectrophotometer measurement, and then we will show a demonstration for how to use the spectrophotometer to measure some solution. Then we can follow the reaction in the solution. So thank you also for Dr. Monica. That's always contact me to organize this event. Then Alhamdulillah, then today we can meet together in this moment. Okay, may I directly to present my slide, or we will invite other student?
So students have joined, so you can share your
Hello?
presentation. So students has joined,
Mhm.
you can share your presentation.
Okay. Okay, let me share my presentation, then we will start to learn about the spectrophotometer in this session. So, could you see my slide?
Yeah, perfectly fine.
Dr. Sal, can you please do it in slide mode,
Hmm? Wait.
in presentation mode?
Yeah. Okay. Little bit delay.
There's a background noise from somewhere, so I request the person to mute himself. Yes, sir, you can carry on.
Wait a minute. Let me try again. Slide. Oke, coba saya Juri pantau saya. Oke.
Uh,
Wait a minute. There is a problem with my slide. Again. Okay. Then.
so the slides are visible, so you can start the slideshow.
Yeah. I already prepare my slideshow, but that's not working in the.
It's okay, you can continue.
Okay. I will continue with this type of presentation, I think. Wait a minute.
Yeah, now it's okay. Yeah.
Okay. Okay. I will start our talk today about the principle, working, and application of UV spectroscopy. We will start from the why we use UV spectroscopy, then very popular for student, also for researcher in the world, because number one, this method is non-invasive method. So will that the method is will not destroy any material because this method is not invasive. So then the other is the economic, then sensitive, also versatile. We can measure solid, liquid, and gases for our sample. So then what is the basic principle in the UV phase spectroscopy? We can see here that there are many wavelengths that we can see here from the gamma and then X-ray, UV, visible, and then other wavelength, so infrared and microwave, and also radio wave and long wave. So in this time, we will focus on the UV phase, UV and visible wavelength in this area. We can see in this slide, then the energy of photon absorbed or emitted during transition from one molecular energy level to another is following the equation. This is the very popular equation, EHC per lambda. Then the E is energy and H is Planck's constant, and then C is speed of light, and lambda is wavelength. So using this wavelength, then we can move to the some transition type of inorganic compound. We can, I think this is very popular in for students. There are 4 type of the transition for organic compound. That is the sigma to sigma star, and then N to sigma star, or N to P star, or P to P star. This type of transition, then we can measure the sample using 4 type of the main transition state. Moreover, then in the transition type of inorganic compound, is that the electron in bonding orbital is excited to corresponding antibonding orbital P star. Then compound containing multiple bonds like alkene, alkyne, carbonyl, nitrile, aromatic compound, etc., will undergo P to P star transition. Then the other is the alkene, generally absorbed in the region of 170 to 205 nanometer. And then the other is an electron from non-bonding orbital is promoted to antibonding P star orbital. Compound containing a double bond involving heteroatom, C carbonyl, CO carbonyl, and C triple bond N, and then double bond O, that will undergo such transition. Then N2 P star transition require minimum energy and show absorption at longer wavelength around 300 nanometer or more. So this is from this rule we can measure some compound, and we can distinguish what type of the transition in our compounds. Moreover, for transition type in organic compound, we also know that there are 4 type of transition. Number 1 is the DD transition. The DD transition for the P acceptor ligand complex is larger than the P donor ligand. And then in the spectra, the DD transition of P acceptor ligand to be of higher frequency than the P donor ligand. In general, though, this transition appear as quickly intense on the spectrum because they are Laporte forbidden. Due to the fibronic coupling, however, they are weakly allowed because of their relative low energy of transition. They can emit visible light upon relaxation, which is why many transition metal complex are brightly colored. The molar extinction coefficient is for this transition around 100. This is a very small coefficient extinction. So sometimes we cannot see this the peak of this transition for DD transition. Then next is the transition type in inorganic compound is LMCT, ligand to metal charge transfer with a P acceptor ligand. So we can see here that the LMCT transition arises because of the low lying energy of the ligand orbital. Therefore, this is a transition from orbital that are ligand in character to orbital that are more metal in character. The electron travel from a bonding p or non-bonding p orbital into a sigma star orbital. This transition are very strong and appear very intensively in the absorbance spectrum. So this is we can see the peaks more larger than the DD transition. The molar extension equation for this transition are around 10,000. Around 10,000. Example of p donor ligand follow like fluorine and then chlorine ion, bromine, and etc. Then the third number of transition type in inorganic compound is the metal ligand charge transfer with p donor ligand. This transition arise from p acceptor ligand and metal that are willing to donate electron into the orbital of ligand character. This is the reason that they are less frequent signs. Metal commonly accept electron rather than donate him. That we can see that metal, this is always choice to accept electron rather than donate the electron. All the same, both type of charge transfer band are more intense than the DD bands, saying they are not laboratory forbidden. Example of DP accepting ligand are following as follow, like carbon monoxide, then cyanide ion, and other double bonds compound or CC triple bonds compound. The fourth type of transition type in organic material is the surface plasmon resonance. This is the currently type of transition type. Then the transition is not exactly transition, but the surface plasmon resonance. It means there is a resonance in the surface of the material of inorganic compound. Then what is the surface plasmon resonance? Surface plasmon resonance is a resonance between light wave and the electron on the metal surface, which generate oscillation. The electron in the metal surface is quantized. So we shortly, the light in resonance with the surface plasmon oscillation. Okay, for the surface plasmon resonance, there are some requirements. For example, the material with free electron. For example, it's metal for silver, and then copper or gold. Then that's plasma frequency in, for example, for lead, indium, mercury, or tin and cadmium. Then the other is the surface or interface, that is a nanoparticle. Then in the right hand, we can see the example of the SPR or surface plasmon resonance from for silver nanoparticle at 420 nanometer. Then the other is the SPR of a gold nanoparticle at 544 nanometer. This is the two example of the surface plasmon resonance type of spectrum. Main principle in instrumentation techniques that we will show today, that the optical spectroscopy is based on the interaction of light with matter. Therefore, the UV phase spectroscopy is a technique based on the absorption of light by an unknown substance or by an unknown sample. The main principle we can see in this slide, that the sample is illuminated with the electromagnetic ray of various wavelength. We can see that the visible ring of the ultraviolet or the part near infrared. The light is partially absorbed depending on the substance. The remaining light, transmitted light, is detected and recorded as a function of wavelength by a detector, and then giving the UV phase spectrum. We can see in this illustration that the light source. Then this is in the middle is the sample. When the light emitted to the sample, then some part of the light will be absorbed, and then some part of the light will be transmitted, and the transmitted one will be detected by a detector. Then this is the specific sample or substance absorb light in different way, then give a unique and specific relationship exists between the substance and its UV spectrum. Therefore, the spectrum can then be used to identify or quantify a substance. So every substance will give the specific spectrum in the UV spectrophotometry. This is the example that we will show today for simple application, qualitative analysis of complex compound, especially in organometallic or in organic chemistry. For example, this is a 110 penanthroline, and then when reacted with the iron 2 plus, then they will give the complex iron, the iron complex. Then we can see the alternation of the spectrum. This is in the right hand is the spectrum of the 110 penanthroline, and then when they react with the iron ion, then they will give the different spectrum. So using this spectrophotometer, UV spectrophotometer, we can follow the reaction of one compound with the other compound. Then the simple application of qualitative analysis in organic compound. For example, in this slide is the reduction of nitro compound, a nitro group from para-nitrophenol to nitro para-aminophenol. In the right side, that using gold nanoparticle as catalyst and sodium borohydride as hydrogen source, then we can follow the reaction using spectrophotometer. Then we can see the difference of the starting material, the spectrum of starting material, the spectrum of intermediate, and then the spectrum of the product. So you only using this instrument, we can follow one reaction from the starting material until the product. Then we can see also the intermediate. This is the other example, same, that the nitro compound reduction using gold nanoparticle, then facilitated by sodium borohydride. Then the other example, this is really I show you that the silver nanoparticle in one extract solution, they can give SPR or surface plasmon resonance as shown in this slide. Okay, then other functional of this spectrophotometer is the for quantitative application. Then we can make a calibration curve by obtained by plotting the absorbance of value as function of the concentration. Using the calibration line, an unknown sample can be determined from its absorbance. So using this spectrophotometer, we can measure quantitatively one substance in our sample. Then this is the reference that I use for this presentation today. Then I will move to the demonstration. I will ask my student to help me in this session. Okay. Okay, we can see in this moment that we will use this type of spectrophotometer. Then, sorry, please come to this. No, the camera, please set up to this. This is the spectrophotometer. Then this is the computer. Then this is the we can see in the slide how to measure the one example, the solution. Then let's start. Come here. Okay. Okay. Please come. Okay. We will measure 110 penantrolene, and then also it's a complex compound with the iron ion. Okay, let's start. Okay, for measurement in the UV phase spectrophotometer, we have to prepare first is the blank sample. We can see here that my student preparing a blank sample using the demineralized water, then insert to the sample holder. We can see here, and then there is sample holder here. Yeah, and then please close. Okay, then move to the computer. Please see. Okay, the first step is to prepare the blank sample. Then we set up the wavelength from 800 to 200 nanometer. Okay, then baseline correction. Always prepare the baseline correction to make sure that our solvent is not disturbing our measurement. Okay, then. Okay, now is the baseline measurement for our blank sample. So little bit time.
Dr. Yudha, can you take the camera a little closer because the baseline is not visible.
Okay, right.
It's better than before.
Okay. Okay, we have to measure the blank. Is it correct to give us the zero absorbance? Then okay, start and blank. Let's give the name. Just blank. Okay, we can see here that this spectrophotometer measuring the blank sample, then we can see a line here that appear in the zero absorbance. Then this is to make sure that our solvent is not disturbing our main sample later.
Toolbox.
Dr. Yudha, is this a Varian instrument?
Pardon me?
Is it Varian? Does the instrument belong to Varian company?
Belong to pardon me, I could
What is the make of the instrument? The UV visible spectrophotometer. It belongs to which company?
Agilent.
All right.
Yeah. Agilent technology. Carry 6 UVs, yeah.
Yeah.
Okay, finish. Then we can see here. Okay, finish. Then we can see here that the line is in zero line. It means our blank sample is okay. Then we can further step to measure the one example of the solution. This is one I think two bpyridine first. Two bpyridine example. Yeah. Yeah.
Sir, we have lost the video.
Pardon me?
We are not able to see the video.
Okay. Videonya putus. Gak ikut tuh. Coba benerin dulu. Taruh. Udah, oke, aman. Kamu fokus aja. Okay, wait a minute. Masuk.
Yeah, now it's visible.
Okay, langsung. Okay, we will start to measure the one solution. Then taruh sini itunya. Kalau nggak mungkin itu. Okay, we start to measure one solution. It's 2 bpyridine. We can see here that same point from 800 nanometer coming to the 200 nanometer. Until 600 nanometer, there is no peaks can be detected here. Okay, we can see here that there are two peaks detected in this sample is 281 nanometer and 232 nanometer. We can see here there are two peaks for 2,2 piperidine. And please remember that there is no peak can be detected from 380 nanometer until 800 nanometer. It means this compound only can be detected in the UV area. So now we will start to prepare a little bit. This is not quantitative reaction, but only qualitative. Then we will react this solution with the iron ion.
So Dr. Yuda, is he your PhD student?
Pardon me, Dr. Sundara.
Is he your PhD student?
Yeah, this is my student.
All right,
Yeah.
He's good at his work.
Okay, we can see. Please add more in this. Tunjukkan ke sini ketika. Nah, okay. When we add iron solution, we can see here that here this is iron solution, and then please take 1,2,2 piperidine solution. Okay, we can see here. This is here is this iron solution, and then this is the 2,2 piperidine solution, no color. No color. Then when we mix these two type of solution, then we can get the red color in the cuvette. Then we will measure this reaction product using this spectrophotometer. Then please measure this solution.
So since there is color now, so there will be a peak in the visible range. Am I right, Dr. Yuda?
Yeah, that's right. That will be coming to the visible area. Okay. Okay, then okay, let's start to see that when two colorless solution we mix, then give us the red color or pink or red color solution. Then we measure this solution. Then we hope that this is the common example for a complex compound formation. We can see here that there is new peak around 500 and 400 nanometer. Okay, finish. Then please use only this or open data. Yeah, we can see here the 2,2 piperidine peaks disappear, and then a new peak in around 500 nanometer appear because we also see that the solution color is a red color. So you can enlarge this one. Okay, scale from 400 or 390. Okay. Then absorbance. This is scale again. Absorbance from 0 to 0.
Dr. Yudha, can you take the camera in the to the front of the screen?
Yeah. Okay.
Probably that would make the peaks more visible.
Jangan ini kan 600.
Is it possible to decrease the brightness of the screen?
Masa sih? Ya nggak apa-apa. Ya 0,7 lebih baik. Harus ini kalau di sini 0,1. Nah, yeah. Okay, we can see here that there is new peak. Could you see this spectrum? I hope you all of you can see this new spectrum, a new peak in the area of 500.
So we are not able to see the peaks.
Okay, bisa di.
And now it is much better, Dr. Yudha. It's much better.
Yeah, this is the new peak from the reaction of 2,2-piperidine and iron. So if we compare this overlay that with open data and then 2,2-piperidine, 2,2-piperidine. Okay, then overlay data. Okay. Okay, we can see here that the green one is the 2,2-piperidine peaks, no peak in around 400 until 600 nanometer. But when we mix this solution with the iron solution, iron chloride solution, then we can get a new peak around 400 until to 600 nanometer. It means this compound 2,2-piperidine already reacted with iron ion to mix iron complex compound. So from this point of view, using this spectrophotometer UV-Vis, we can learn about the reaction of one compound with the other compound, and then we can measure the reaction product. And then after this, we can also quantitatively measure how the yield the reaction product. So this is the one example I show in this moment, reaction between 2,2-piperidine with the iron ion to make the iron complex compound. Then I think that's all. And then please, if there is a question for this moment. Thank you very much.
Thank you, sir, for conducting such an informative session. Do we have any queries from the students or the panelists? If there are any queries, they can be posted in the chat box. Yeah, Dr. Yudha, I have a small query. Am I audible, Dr. Yudha?
Yeah, okay, please.
Dr. Yudha, can you also do the temperature dependent experiments? Does the instrument have a Peltier accessory?
Unfortunately, no. This spectrophotometer is only for room temperature measurement.
Okay.
We cannot set up for the different temperature.
All right. And do you study? Do you look at proteins folding also with this instrument? Have you ever tried? Has anybody ever tried studying protein unfolding using UV visible spectroscopy at your place?
Pardon me. To study what type?
Like we look at protein folding and protein unfolding. So have you ever has anybody ever tried in your department using this instrument for looking at protein folding? Have they ever tried?
No, not yet. In our department, never. No, I think there is no researcher here study about that.
All right.
Yeah.
So Dr. Monica, anything from your side?
Yeah, I'm audible.
Yeah, you are audible. Yes.
Okay, sir, I just want, I'm just representing my students. So can you just give us a brief on the basic principle of UV spectroscopy? Because students are from MSc and from BSc too.
Okay, that's the brief for the UV phase spectroscopy that I already show you in my slide that when the light is emitted, then attack to the one sample, for example, a solution, then some part of the light will be absorbed by the sample, and then the other one will be transmitted. Then the transmitted light, it will be detected by the detector. Then the detector will give us a specific spectrum. Then we can read it, the spectrum based on the known rule. For example, that for organic compound, there are 4 transition state that from the N to P star, for example, then wait a minute, I will show in. Okay, from sigma to sigma star, and then N to sigma star, or N to P star, and also P to P star. So for organic compound, there are 4 type of transition state. Then for inorganic compound, until now, maybe will be developed again in the future. Also, there are 4 type of the transition state. That is the DD transition, and then ligand to metal charge transfer, or metal to ligand charge transfer. And the current finding is the surface plasmon resonance. This is 4 type of interaction between the light and the sample or the compound. In our sample, we'll give 4 type of transition in organic compound or in inorganic compound. So based on this interaction, we can measure or we can get the spectrum, and then we can analyze them to give us information about our compound, and then how much this compound is contained in our sample. So based on our experience, using this spectrophotometer, we can get more information about also mechanism reaction. We can follow our mechanism reaction, and then we can also detect the an intermediate for organic reaction. I think it's clear for your student, Dr. Monica.
Yes, yes, sir. Sir, I just want to ask a question. Like we have a complex, we have a metal complex, coordination complex, and the metal and the ligand is forming back donation, is forming a back donating bond. So in this case, what should we infer, that the transfer metal to transfer ligand transfer is there, or from ligand to metal transfer is there, so that our student can understand it more clearly?
Yeah. Okay. So in this case, there is a donation back from the metal to ligand. Actually, the complex compound is mainly a form by donation of electron from the ligand to the metal, but the metal also can be can donating back the electron to the ligand. We have already known that the ligand is the Lewis base, then they will can give electron to the metal as acid, Lewis acid. Then the Lewis acid, the metal will also give the donating back of the metal. So there is 2 type of charge transfer: ligand to metal charge transfer, also the metal to ligand charge transfer. So in this spectrum, we can see 400, around 400 until 600 nanometer, the new peak for 2 bipyridine and iron ion. That's especially for ligand to metal, and also supported by the metal to ligand charge transfer. That's all, Dr.
Yes,
Monica.
sir. Yes, sir. Sir, one more question has come from the student, that what will be the spectra if we have a long conjugation?
Pardon me.
Conjugation. I think he want to ask a question like this: that if conjugation is long, alternate double bond, single bond, this conjugation is long, then what will be the spectra? UV visible spectra. So what kind of transition? Maybe he's asking for what kind of transitions are there?
Yeah, that's for long conjugation, especially in organic compound. So we cannot distinguish by only measurement, but actually there is some rule we can calculate first to predict where the peak will be appear in the UV spectrum, including the long conjugation compound. I think we have to measure, to calculate first, then we can predict where the peak will be appear from our sample.
Sir, can we do like this, that chromophore group is there? How can we distinguish it from other group? If we add a chromophore group to a moiety, organic moiety, and I think UV that the peak changes its place, right?
Yeah, that's true. For the other chromophore, the UV Arya will be give more detail of the type of conjugation, also the new chromophore if we attach new chromophore in our compound.
Anurag sir, thank you, Yuda sir. Anurag sir, no more questions students has given me right now.
All right. So thank you, sir, for conducting such an informative session as always. And we end the first session of this workshop, and we should
Okay.
be joining again at 3 p.m. Indian Standard Time to attend the second session by Dr. Muhammad Abid, who will deliver a tutorial session followed by demonstration of flash chromatography.
Okay.
So see
Yeah.
you
Thank
soon.
you, Dr. Anurag. Yeah. Thank you, Dr.
Thanks.
Anurag and Dr. Monica. Yeah.
Thank you, sir. Thank you so much, sir. Sir,
Thank
hope
you so much.
you will join our second session also. And please ask students from your side to join again.
Okay. Sure.
Thank you, sir.
Okay. Thank you very much.
All right. So we all meet at 3 p.m. Thank you. Good afternoon, sir.
Good afternoon, Dr. Anurag. How are you?
I'm good, sir. So you had your lunch?
Yes, all done.
Okay.
Thank you.
So is the canteen near Bhopal ground still active?
No. It's all vanished because you have not seen this Bhopal ground otherwise. So everything is vanished. So they have cleaned up that area and they have other things there. You know,
Okay. All right.
it's all under Jamia Millia Islamia. Otherwise, they were all were encroachments actually. So it took long time to remove all these encroachments. But
Okay.
finally, yeah, it's good now.
Yeah. There was a big canteen near Bhopal ground when I left the college.
But now they have a big canteen, the central canteen inside the campus actually.
All right. Near Ansari Auditorium, is it? Near Ansari.
No. It's very near to this Galib statue, the gate number 7.
All right.
It's near to Theoretical Physics Center.
All right.
Yeah.
Got it. Yeah. I had a great time in Jamia.
Yeah, I know. Yeah. It's good to see our alumni doing really great in different parts of the world. Yeah, it's really good.
Yeah, thank you, sir.
So when did you join Amity?
I joined 7 years back, sir.
That's great. So your specialization is what?
It's protein biochemistry.
Protein biochemistry. So you did your PhD with Vedant, sir?
No, sir. I did my PhD in IIT Delhi.
Oh, okay.
I work with Professor Shashank Deep.
Okay.
So he works on protein folding, protein aggregation, and so on.
Okay, that's good. So still you are continuing your research in Amity?
Yes, sir. It's
good. So you have all the instruments which are required, like CD or fluorescence and
we do not have CD, but we do have fluorescence with the Peltier accessory.
Okay, for at different temperature to measure.
Yes, sir. We do have DLS, zeta cycle, and FTIR. And
so when did you visit Jamia last time?
I think I came around 1.5 years back, and I met Lukman sir.
That's okay.
Yeah, Shagir bhai. So we.
Okay.
Yeah. So मैं आऊँगा sir. I'll come again. I'll meet you.
Please come and you can also have a visit in our central instrumentation facility as well as departmental instrumentation facility. So we have lot of sophisticated instruments, especially in CIF. So if you need any help, so definitely we will all are there.
Yeah, thank you, sir. So, sir, Asim was co-guide to my student.
Okay, Dr. Asim is working on protein folding and
Yes, sir, protein aggregation.
Yes, protein aggregation.
मेरे student थे इशफाक ने आसिम के lab में काम किया.
Okay, that's good. Yeah, because you can collaborate with him because he is working in the same area, right?
Yes, sir.
And they have all the facilities starting from protein purification to ITC and then CD.
Yes, sir.
Fluorescence. They have all the instruments in their lab actually.
Yes, sir.
Because it was all with the help of Professor Faizan Saab, because he got a lot of instruments, he got
Yes,
a lot of funding. So
Yes.
he managed to get these instruments in, long back. So still these people are working on these instruments and they are getting benefited, right? And
Yes,
that's why they are publishing a lot of papers every
Yes,
year.
sir. Yes, sir.
Yeah.
So we call Professor Faizan Ahmad Bhisham Pitamaha of biophysical chemistry. Yeah.
He was that figure only, yeah, because
Yes.
he established that protein chemistry is a big group now. Dr. Imtiaz is there. He joined from AIMS. He came from AIMS, so he's leading this group actually. So they are publishing a lot of papers and good quality paper actually.
Yes, sir. Yes, sir.
Yeah.
Yes, sir. Yeah. It's good to have you, sir. It's good to talk to you.
Nice to talk to you, sir. Nice.
So Dr. Monica, shall we wait for a few more minutes before starting? Dr. Monica? I think, Dr. Monica, am I audible? Sir, I think 1-2 minutes wait karte hain and then
It's okay. It's okay.
Yes, sir.
So the participants are mainly master's student, right?
Yes, sir. So they are master's students of biochemistry, chemistry, and forensic science.
Okay.
Dr. Bhuvnesh, shall I start or shall we wait for a few minutes?
We can start, sir.
Okay.
I think Seema ma'am is not there.
I think we can start. You know?
Okay.
I think in the meantime, she would join.
Yeah.
All right. Just a moment. All right. So before, so good evening, good afternoon, everybody. And just a moment. Before starting the next session, let me give a brief introduction to Dr. Muhammad Abid. Currently, he is Assistant Professor, Department of Biosciences, Faculty of Natural Sciences, Jamia Millia Islamia, fondly called as Shehre Arzu Mera, Dayare Shauq Mera. His research interests are in the areas of synthetic organic, bioorganic, and medicinal chemistry. He was awarded UGC Raman Postdoctoral Fellowship for working at Epley Institute for Research in Cancer and Allied Diseases, University of Nebraska Medical Center, Omaha, USA. He also received a postdoctoral fellowship to work in the Laboratory of Chemistry and Biochemistry at University of Paris. He has held multiple research grants as PI and co-PI from SERB, DST, and also UGC, and he has filed multiple patents of high commercial value. He's a member of some very prestigious societies like ACS, Royal Society of Chemistry, and Society of Biological Chemists India, to name a few. I request Dr. Muhammad Abid to please unmute himself and conduct the tutorial session followed by the demonstration of the technique. Over to you, sir.
Thank you, sir, for introducing and for your kind words. And are you able to see my presentation? Is it visible
Yes,
to all of you?
Yes, sir.
Am I audible?
Yes, sir.
Okay. So thank you so much. And I'm thankful, really thankful to be part of this a very important workshop, which is on instrumentation techniques. So I'm really thankful to all the organizers, and my special thanks to Dr. Monica for inviting me and for giving me this opportunity to share, my ideas about, some basic concept of flash chromatography. And before going into the the technical details of flash chromatography, let me introduce about the chromatographic techniques, especially the liquid chromatography. Because when we talk about the flash chromatography, we are talking about the liquid chromatography, because in this type of chromatography, we use two different phases. One is the stationary phase, even in each any chromatographic technique. So one is the stationary phase and other one is the mobile phase. So in liquid chromatography or flash chromatography, generally we use the stationary phase is a solid phase, which is generally silica or alumina. It depends on the type of compound or the nature of compound which we are going to separate or purify. And the most commonly used is the silica gel, right? So and the mobile phase is generally the mixture of solvent. Generally we avoid alone a single solvent. Generally we use a mixture of solvent, and the mixture of solvent is made in such a way that one of the solvent is highly polar and the second solvent is less polar, so that we can make a gradient, right? So that we can have a good separation of different components of a mixture, right? So now if you look at the evolution of these liquid chromatographic techniques, the first one is the thin layer chromatography. And then the thin layer chromatography, actually it uses a plate, or it uses the silica gel which is absorbed on a solid phase. Like it can be a thin layer TLC plate, like aluminum sheet plate, which is coated with fine layer of silica, right? So this is one of the most commonly used technique in in chemistry or even biochemistry lab. So when we talk about the organic synthesis or any chemical reaction, we cannot think about any pure compound without talking about the chromatographic techniques. So these chromatographic techniques are so useful that we cannot have any chemical synthesis completed until we use any of these techniques. So the first technique which generally we use is the thin layer chromatography, in which we put our the spots of the reaction mixture which is undergoing, and then we can look at the progress of the reaction. So thin layer chromatography helps us to show the progress of a chemical reaction, and easily we can find whether our reaction is completed or it is still going on. We have to leave the reaction for some more time. So it can be checked with the help of thin layer chromatography. So it has very important role in the in doing any chemical synthesis. Then we have another technique which is the plain column chromatographic technique, which is again most commonly used in chemistry labs. And in this case we generally use a glass column, and this glass column provides the support, and then we add we pour into this glass column a suitable solid phase, that is silica gel. And the length of the silica gel, how much silica gel we have to pour into the column, that is also very important. So we have to we have to calculate the amount of silica gel which is need to be poured into this column on the basis of the amount of compound which is going to be purified, right? So on the basis of the weight of the mixture, the compound which need to be purified, we will accordingly we will change the amount of silica gel. Then once this silica gel is settled in the column, and then we will add our compound of interest, the compound of interest which is going to be purified, right? And generally whenever we do a chemical synthesis in a lab, generally we almost all chemical reaction will give you more than one product. It's really very rare that we get only single product at the end of the reaction. Generally we have some kind of impurity that may be the unreacted material, or there may be some side reaction, or there may be some other impurities coming during the reaction. But every time we need to purify the the compound through column chromatography. Once this compound is purified through this column chromatography, then we can subject this compound to various spectroscopic techniques, like like UV or IR, or then proton NMR, then 13C NMR. then mass analysis, then elemental analysis, then X-ray crystallography if we have the single crystal structure of the molecule. And with the help of this much of data, we can confirm that the compound which we want to prepare, it is finally confirmed. So this is how much efforts a chemist put in making just a single molecule, right? And should be novel compound, right? If it is novel, then you have to do everything, right? If it is known, then you can compare the data with the known, and you can once the data is in line with the reported molecule, you can say that you have confirmed your synthesis. But you have to use all these techniques, right? Then the chromatography techniques was advanced, and in the advanced form it came into the flash chromatographic form. So flash chromatography, it was introduced in 1978, so it's not a new technique, but at that time
Background noise from somewhere.
should I continue?
Yeah, yes, sir. Please wait.
Okay, so this in the flash chromatography. So if we look at the difference between the column chromatography and the flash chromatography, so flash chromatography we use an external pressure. So when we put external pressure into this column, then it will help to increase, that it will reduce the size of separation. It will reduce the time, how much time it is taking to separate the molecule. So it will reduce the time actually. So flash chromatography, it is also known as medium pressure column chromatography, because we use external pressure in the column chromatography to have the fast purification, and also once the purification is fast, and it also reduces the time, it also increases the quality of the separation, and also it reduces the cost also, right? So in the case of flash chromatography, we need not to use lot of solvent in only 100 or 200 ml of solvent. We can purify our molecule of interest, right? Then when we go up to higher pressure liquid chromatography, then we have HPLC and then UPLC, which is the most advanced form of HPLC, right? So they all are the different phases of liquid chromatography. They are the different techniques, and so we want to get more information about flash chromatography. Let us talk about the classification of chromatography. So on the basis of the shape of the silica gel, or the shape of the stationary phase which we are using in the column or in the chromatographic technique, we can classify the technique into column chromatography, which also includes flash chromatography. Or we can have another type, which is planar chromatography, which includes the TLC, HPTLC, or the centrifugal TLC, right? Then on the basis of mode of separation, we can classify all these chromatographic techniques on the basis of adsorption. If there is adsorption of molecule on the adsorbing medium. So what happens in the case of column chromatography or flash chromatography, we are using a stationary phase, which is actually the silica. So because it's a stationary phase, so when we add the solvent into the column, so what happens, the molecules which are present in the mixture, they will adsorb on the adsorbing medium, that is the silica gel. So they will be adsorbed by silica gel, and they will be eluted on the basis of their polarity, right? So that is the adsorption chromatography. So column chromatography is also known as the adsorption chromatography, and on the basis of polarity, the molecules are separated. Then we have the partition chromatography, where the separation of molecules takes place on the basis of the partition coefficient, their polarity, and the solubility parameters, right? Then we have the ion exchange chromatography, which is actually based on the size of the molecules. So on the basis of the size of the molecules are separated, And similarly, we have the size exclusion chromatography and affinity chromatography. So these are the basic, the classification of chromatographic techniques. And on the basis of mobile phase also, we can classify the liquid chromatography and the gas chromatography. Then these are the various forms of chromatographic techniques.
Sir, I'm sorry to interrupt you. Can you start the slideshow?
It's okay, sorry. Is it okay now?
Now it's in the slideshow.
Okay, sir. Sorry. So these are the various forms of chromatographic techniques. The column chromatography, which also includes the prep column chromatography, the flash chromatography, then the vacuum liquid chromatography, and so on. Then we have the pressure liquid chromatography, where we have the separation of mixture on the basis of the high pressure which is introduced into the chromatographic machine. That is the HPLC, which requires high pressure, right? And then we have the normal phase and the reverse phase chromatography. The normal phase is the column chromatography, which we generally use in the lab, and reverse phase is when we reverse the the phase of the column, in which we use the water as well as a mixture of solvent along with the water. So it becomes a reverse phase chromatography. But generally in organic lab, we do the normal phase chromatography. So when we talk about the column chromatography, we can pack the, so once you look at the pictorial representation of the columns, so in the first picture you can see that this is the column which is pre-filled with the silica gel of desired amount, right? At the top of the column we have put some small cotton, so that the level of silica is not disturbed, right? And then now how to load the sample onto this column. So the first step is we have to fill the column with silica gel alone, and then we have to settle down all this silica gel with the help of a non-polar solvent. So initially we use hexane, which has the zero polarity, so that there is no only the non-polar solvent is introduced, so that we have the non-polar column ready. Now once this column is ready, what we are going to do, we will introduce some little amount of solvent, and then we'll pour our compound. Now to pour this compound, we have two different techniques. One is the wet technique, in which what we do, we dissolve our mixture of compound in minimum amount of solvent, and this solvent must be non-polar. If it is non-polar, this is best, because it will not interfere with the column. If you take a high polar solvent, then it will create some problem. Let's see, if you dissolve your compound in high polar solvent, then what will happen? Once you introduce into the column, it will start going down, because with the high polar solvent it will move very fast. That's why the high polar solvent are generally avoided, and generally we use less polar solvent. Or in the best case scenario, what we can do, we can use the same solvent system in which we are going to run the column, right? So this is actually the introduction of the sample. This is the best way to introduce the sample onto the column. This is, you can see, this is very uniform, and your all mixture of sample is present at the top of the column, right? The other way is, you can take your compound. Let's say your compound is in the liquid form. What you will do, you will add silica gel, the same silica gel which you have used in the column, in the making of this column. So you will use the same silica, and you will absorb the whole compound onto this silica, and you will add that much of silica, so that this compound becomes a fine powder, right? So once it is finely powdered, a powder converts into a powder, then you can pour that powder on top of this column, right? So in that case, you will have, instead of liquid, you will have a solid colored silica, which is pre-adsorbed with the compound, right? Now once this column is is ready for the purification, what you will do, you will start the column with the non-polar solvent. Why we start the column with the non-polar solvent? Because with the non-polar solvent, whatever the impurities, whatever the non-polar impurities are present in the mixture, they will be eluted first, right? So now you can see it's very clear that when, and slowly you can increase the polarity of the solvent, right? And generally the solvent is not used alone. Generally we use a mixture of solvent. So initially we will use the non-polar solvent, that is hexane or cyclohexane or n-pentane or a petroleum fraction. They all are the, the available options for non-polar solvent. So once you pass, let's say you have passed 50 ml of non-polar solvent through this column. So the whatever the spots are there, whatever the the compound is there, it will not move until it is non-polar. If it is non-polar, it will move and it will go out first, right? So this way you can remove the non-polar impurities in your compound. Then what you will do, you will slowly increase the polarity of the solvent mixture. And in this case, you will add some polar solvent into the non-polar solvent, which means that you are using two different types of solvent. One should be non-polar and other should be highly polar. And you will make a mixture in such a way that let's say you are making 100 ml of a mixed solvent mixture. So you will use, let's say 95% of non-polar, let's say it is hexane, and 5% of, let's say it is ethyl acetate. So ethyl acetate has the polarity of, it's approximately 3.5. So what will happen? Once it goes, this solvent moves in through this column. Thus the whatever the different the components are there in the mixture, they will start slowly moving. And you can see this pictorial representation of the column chromatography. They will come, and as soon as you add this the solvent of desired polarity, and finally you can get the purified compounds. So because it's a mixture of more than one component, so you will not collect all the the element which is coming out from this column, you will not collect in just one beaker or in a test tube. Rather than you will collect just 5 to 10 ml of each fraction in a test tube, so that you can confirm. And in the later stage, what will see, this is another representation. Let's say you have 3 components in the mixture, so it will start going like this, and finally you will have all the 3 fractions. Now how to confirm these fractions? So once you have all the fractions in your test tubes, and you can put a TLC, thin layer chromatography, and you can use the pre-coated TLC plates, and you can put all your spots in serial wise, and then you can see what test tubes belong to the same fraction, and you can collect them, and you can combine them to make one fraction, right? So this way you can get 3 different compounds which eluted from this column. Now the next challenge is how to confirm these molecules. What are these compounds? So if all the 3 compounds, they are if all these compounds, they are it is not matching. If you put a TLC plate, in your TLC plate, you must be able to see the different different spots in a TLC, right? So number of spots corresponds to number of compounds or number of products in the reaction mixture. So let's say you have 3, you are getting 3 different I can show you TLC. Yeah, see, this is a pictorial representation of a TLC which we have seen, right? So see, in this TLC plate, you can see so many spots are there, and you can confirm these spots by putting your the sample which you purified after purification. You can put them also, and you can collect accordingly what fraction belongs to which spot, and then you can collect in a different spot. Now, if any of these spot is matching with the reactant molecule, then you can you can reject that part, you can reject that fraction, because it is nothing but your unreacted material, right? because you are more interested in that spot which is a new spot, which is not matching with your reactant. Let's say you have added 2 reactant molecules and you are getting a final product with 4 spots. In your TLC, 2 spots belongs to your 2 reactant and you are getting 2 new spots, right? So these 2 new spots, we have much more interest in these 2 spots. So we will separate these 2 spots, we will collect these 2 spots, and we will check through different spectroscopic techniques, because the column chromatography will give you the pure component in a mixture. Once you get a pure component in a mixture, this is one job which is done as a chemist, right? The second job, which is more important, to confirm what is that spot, what is the chemical which is present in this spot and what it should be. If you are expecting some molecule, so you must know the molecular weight also, right? So because if we plan a chemical reaction, so we know that we will mix A and B and it will give you a product C, but also the product D, which is the side product, right? So we are more interested in product C. So we know very well what should be the expected molecular mass of product C. So what will be our next strategy? Our next strategy will be, we will concentrate the fraction which is of our interest, which is unique, which is not matching with the reactant molecules, but it is a unique. So we will concentrate that fraction, we will try to solidify it, and then finally we will submit 1 milligram of that sample to the mass spec. So mass spec person will give you idea about the mass of that component as well as the purity also. So once you get the purity analysis, you will be very happy to see how much efforts you have put it and how much purity you are getting. If you have done everything in the right manner, and your selection of solvent, your selection of silica gel, your column selection is good, then definitely you will get the sample of your purity of your interest with more than 95% purity. I myself, I trained my students, so I always see, before going to any spectral data, first I look at the purity data of that sample. If that sample is pure, if it is more than 99% or it is more than 95% pure, then only we can go for any spectral characterization as well as the biological activity, right? So this is one part, that is the column chromatography. So column chromatography take care of the purification of our compound which we are making in the lab, right? This is actually the difference between thin layer chromatography and the column chromatography. In thin layer chromatography, we generally use pre-coated alumina sheets which is coated with silica gel, and you can see the spots. The red and blue spots, the green spots, they belong to 2 different compounds. Let's say these 2 spots, they are unique spots, they do not correspond to any reactant, then we have interest in both these spots. Now just by looking at the size of these 2 spots, you can say that this red component is in major amount, and the green spot is in the minor amount. So you have 2 components you have 2 compounds which are formed in your reaction, and you can see that one is major product, another one is the minor product, right? But if it is minor product, and still it is new, then still we have so much interest what is there in the spot, green spot, right? So this is the column chromatography. They will look like this in the column, and then finally you can collect in the test tubes, and every time you have to change this test tube so that you can have the pure sample at the end of the column chromatography. Generally what happens when you do column, so let's see this column. We have 3 different spots, and when you collect these 3 spots, it generally happens that between 1 and B, but let's see, you got your component A, it's finished, and your component B starts coming, right? So in that medium time, in that buffer time, what will happen? There will be some amount of the fraction which contains both A and B component. So in that case, you will collect that fraction in a separate test tube or conical, and that will be a mixture of A and B, right? It generally happens actually in the column chromatography. Generally, it always comes that you are losing your compound. Let's say it is A or B, both are your compound, but you are losing some of your compound in the form of mixture. But you don't discard this mixture, because if your sample A is confirmed that this is your desired compound, so again you can run the column of this mixture of A and B, and then again you can collect the pure sample, that is A. So there is no need to purify again and again, but when you are getting a mixture, you can collect all the mixture, and you can also run one more column, so that, but that time the column will be very thin. So the width of the column is also very important. You cannot take every time the very big column, or you cannot put high amount of silica gel, you cannot put large amount of solvent into the column, because that is always the wastage of money, that wastage of time, the wastage of resources, right? So in that case, what we have to do, if you have some amount which remain unpurified, so in that case you will use a very thin column, depending upon the amount of mixture, but what you have left, which is unpurified, which is impure, right? So this is again the pictorial representation, how the spots they are coming and how they are moving. Generally, because this is towards the gravitational force, so the more polar, if your sample is having very less interaction, or it is less absorbed with the silica gel, it will move very fast, it will come first, right? If it is having medium interaction with the absorbing media, it will come in the medium phase, and then the compound which is having maximum interaction with the silica, it will move very slowly, and it will come at the end of the column, right? So detection of the column we can do with the help of TLC. Then we have seen that the difference between the thin layer chromatography, the techniques, the difference between the two techniques, and then what are the different factors which can affect the efficiency of the column, right? Again, these are the same parameters which I am telling you, that the dimension of column is very important, the particle size, because silica gel is not just one silica gel which is available in the market. There are so many silica gel of different mesh sizes. So depending upon your requirement, you can order such silica gel, and then you can use that particular silica gel. You cannot use any silica gel for any column purification. For example, if you have an acidic compound in your sample, then you have to use a silica gel appropriately, and also you have to use a little amount, a few drops of a base, so that an acid is not having any interaction with the silica gel. We know very well that silica gel, which is generally used in the column chromatography, it is acidic in nature. So to avoid any interaction of the acid with the column, so we will add some base so that there will be no interaction. And then the temperature of the column, generally we do the column at the room temperature. If the temperature is very high, in that case your solvent will also evaporate very fastly, right? So it's better to have the room temperature where you are running the column. That will increase the efficiency of the column. Then the packing and the quality of solvent. So the quality of solvent is also very important. The selection of solvent is also very important. So in the column chromatography, we are not using any pressure, but if we use pressure, it becomes the flash chromatography, and it increases the efficiency, and also that it takes much less time as compared to the column chromatography. So these are the few important applications of column chromatography. We can use from the organic synthesis to medicinal chemistry to drug synthesis to drug formulation to the natural product isolation, then removal of impurities. It is the best part is it can also be used in the separation of diastereomers. We know very well that enantiomers cannot be separated through column chromatography, but diastereomers can be separated through column chromatography, because diastereomers, they have different boiling points, and they have different physical and chemical properties. So they will be seen in the column chromatography at different places. They will not come at the same place. But what happens in case of enantiomers, because enantiomers are the two different forms of the same compound, they have only the difference of the rotation of plane polarized light into clockwise direction or anti-clockwise direction. So they have no difference. So if you put a TLC of two enantiomers, they will come exactly at the same position because they have the same physical and chemical properties. So it's really difficult to separate a mixture of enantiomers through column chromatography, even through flash chromatography. But we can separate a mixture of diastereomers through column chromatography as well as the flash chromatography, right? And natural product, the natural product chemistry also, it is very, very useful. But in natural product isolation, generally we use a very big columns, because in that case we are using the crude material, that is the crushed leaves, or the different parts of a plant, and they are very in very large amount. So in that case we have to use such big columns, and in that case we have to use a lot of amount of solvent also. So that is very laborious work, that is very expensive also, because you require a lot of solvent drums, and they are very expensive. So but with the help of this column chromatography, we can do the isolation of active components of a plant extract, right? And if we want to do confirmation of these active constituents, again we can go for the purity and then the mass, and then finally for the spectral characterization like UV or IR or the proton NMR or the 13C NMR or the mass or the spectral or the the X-ray crystallographic analysis. So all these techniques will come later, but this is actually the first part in a lab, that we should purify the mixture which we are getting at the end of a chemical reaction, and it should be pure enough to do any analysis. And also if we go for biological activities, we should be very much clear about before going to biological activity, our sample must be very much pure. Otherwise there will be no use of doing any biological activity, and even it is really difficult to publish that work also, right? So these are the advantages. The same, we have the choice of mobile phase. We can use a lot of we have different combinations of mobile phase. Mobile phase is nothing but the mixture of solvent which we are using. We can use the solvent in the isocratic form or the gradient form. So what is isocratic form? That is, we are using the same percentage of solvent throughout the column, throughout the the separation, throughout the purification. Let's say we are using 95:5 mixture of hexane in ethyl acetate. So we'll start the column with this composition, and we will end up with the same composition, that is isocratic. But the gradient, in the case of gradient, what we will do, we will slowly increase the polarity of the mixture, so that we can have a better, we can have the better separation. So it depends. It is not necessary that we should go for isocratic or gradient. It depends on your sample, what you are going to separate, right? So we can separate any type of mixture, especially the organic compound, or it may be the metal complex. We can do the purification, but in that case we have to take all precautions for that, the metallic complex. The disadvantage of column chromatography are it is time consuming. If you start a column in the morning, if you have a large amount of, let's say it is 1 gram or 2 gram sample, or it's a 10-gram sample, it will require a whole day for doing the sample purification, because you have to collect every time you have to change the whether it's a conical or a test tube, you have to change every time. And then you have to, then again, once you have all the test tubes in all your fractions in test tube, then you have to confirm which test tubes belongs to the same component or same fraction. Then you have to confirm this through thin layer chromatography. Once it is done, then you have to go for Bookie evaporation, then you will remove all the solvent, then so that you can convert the solvent phase into your solid sample, and finally you will get your final compound. So it required a lot of time. So at least one day you require to do this exercise. The mobile phase is required too much because every time you have to pour 100 ml or let's say 200 ml. So in a typical column chromatography, you need approximately 500 to 600 ml of the mobile phase. So they are very expensive. They are sometimes they are carcinogenic also. So it is also very dangerous to health also. That's why we avoid the use of benzene or toluene or such type of aromatic solvents, because they smell, they have very high smell, and then they cause so many problems, right? So we generally avoid such aromatic solvents, and that's why we use the petroleum ether or petroleum fraction. They are less harmful, but they are very expensive. So it require a lot of amount of to purchase these solvents. And then the automation is it's possible. So when we do automation, so we come to the flash chromatography. Actually, I want to make some basis, the foundation, so that you can easily understand why this column chromatography is so important. Because if you have no idea about the column chromatography, then it's really difficult to understand the flash chromatography. So is it clear to all of you? I'm just asking the students if they have any queries regarding column chromatography.
Yeah, I think you made it very clear, Dr. Abid.
So should I continue?
Yes, sir. Yes.
Okay. So now come to the flash chromatography. Flash chromatography was introduced because of the same reason, because we have some disadvantages of column chromatography. We are expending a lot of money on the mobile phase, on purchasing the solvents, the mixture of solvents. So when we talk about the mixture of solvents, so we have to purchase every time the drums of solvent, 25-liter drums of each solvent. It should be there in the lab, so that you can make any mixture of any percentage of these solvents. It's time consuming. To improve the efficiency, to reduce the cost, to reduce the time, this technique was introduced, right? So in this technique, what they have done, they have used slightly smaller silica gel particles. Generally earlier it was 250 to 400 mesh, but they have used even less than this silica gel particles. The smaller size of this silica gel particles, like 100 to 160 mesh also they have used. So they reduce the silica gel particle size, and also they use the pressure. So they introduce pressure into the column, and it may go up to 300. So the latest machine which is there in the market, it can give pressure up to 300 psi. And you can imagine that how fast is the purification by using these techniques. I have the machine in my lab, and that machine is actually provides up to 150 psi pressure. That is also very very good, because it gives in 1 minute it is giving 50 ml of the eluent. It is coming out through this flash chromatographic machine. So even in half an hour you can finish your job. And but again you have to do the same thing. What that you have to collect all the fractions. But in this machine, what is the best part, that this machine will tell you the fraction number. Let's say it is fraction 1 to 30. So fraction number 1 to 10, it belongs to the same peak. So you can see the peaks also, right? So I can show you the machine. This is your machine. So in the machine, you can easily see, let's say you just put it your sample. This is the column which is outside, and this is all the pressure building machine is there. And then you have the collector is there. It is having this is the rack, and it is having almost 30 test tubes in the rack. And this is actually the collector which is giving the the fraction into each, and every time once this one test tube is filled, it automatically it will it will change its position. It will go from one to second test tube, then third, and so on. And finally, once all the fractions are collected, from this graph you can easily see that fraction number 1 to 10, they belong to the same peak. It means they are the same compound. If you want to be very sure that before combining all the fractions from test tube number 1 to 10, what you will do, you can even cross check by putting one TLC for spot 1 or spot 6 or spot 9, so you can further confirm whether the machine is telling the truth or no, it's the right or wrong. So you can see, because each peak will give you number of test tubes, and these number of test tubes will easily can be seen through this the screen. It will tell you that which test tubes belongs to which the peak. Each peaks corresponds to one component, right? So through these peaks you can collect it. It is actually the basis of this flash chromatographic machine. It will show you the peaks, and finally after purification you can confirm, and then you can concentrate, and then you can submit for the LCN mass analysis, right? So this is actually the instrumentation part. It has the pump system, which is and in the pump system you can control the the how much pressure you are giving. That is also it is there. Then you have the the column. Generally we have glass column, but in this case in the in flash chromatography generally we use the plastic columns. They're already pre-filled columns, and also the empty columns are there. You can use these empty columns. See, these are the columns. This is one of the column. So you can they all are filled with the silica gel of the same quality which is required for flash chromatography. And then you can put your sample at the top of this silica on the top of this column, and then it will separate out through this machine, and finally you will get all the components which are present in this mixture in your test tubes, right? So generally we use the preloaded columns are there, which are provided by the company. I have so many. So once we have the live demo, then you can easily see the machine. It will be very easy to understand when you go for live demonstration. It will be very easy to understand. So we have generally we avoid glass columns. We have the plastic columns, or we have the the steel columns also, but they are very expensive. Then we have a pre-column generally, which it is also known as the guard column, so that it can avoid any mixture. So that if you use a pre-column along with the column, then it will increase the length of the column, and also the separation of the components will be very clear. It will be very good also. And then we have the fraction collector, where we have the test tubes at the rack, which is containing 30 test tubes, and you can get all your fractions collected there. And then finally detector is there, and chart recorder is there, which is on the LCD display, and you can see what is actually happening in the. So whatever is running the column, you can easily see that which fraction is coming right now. It can be easily seen through this LCD display, right? And then these are the technical details. So we have a technical person from the company. So I purchased this machine from Teledyne USA, and it cost me around 10 lakh rupees. And so we have a technical person which came from the company which they provided us, and they will have a technical session. They will explain you about the quality of columns, the the sample injection, the all the columns, the types of columns, what are the advantages and the disadvantages of these things, right? And finally the application. Again, application is it's almost the same like we have in case of column chromatography, but in this case we have the fast purification, and also the isolation and purification of different flavonoids, or different flavonoids or alkaloids, or different components of a plant extract we can do with the help of flash chromatography, which is not possible with the help of column chromatography. Because in flash chromatography we have the detector also, which is attached. That is, the UV detector, we have so many options there, but in our case, we have the UV detector. So if your compound is UV active, it will show you a clear peak in the in the LCD display. If it is not UV active, then we have to check through through different we have to check through TLC, but we have to develop that spot with the help of some developing reagent like carbohydrates, which are not seen in the which is not possible to see in the column chromatography or the flash chromatography. So we can char and we can use the sulfuric acid to see, so we can develop the TLC and we can see which fraction is coming. So especially it has very much applications in the flash chromatography in the natural product isolation, the different isoforms of different natural compounds, right? And obviously in the organic synthesis. So it is the best part that any molecule which you are synthesizing in the lab, it can be purified by using the flash chromatography. So it's an advanced technique. It's an advanced technique. We can if someone asks you why not HPLC, HPLC is also high pressure liquid chromatographic technique, but it's very expensive. It costs around 20 to 25 lakhs. It's very expensive, one part. And second thing is, which is also important, that it generally run in the reverse phase, and also you can purify a very small amount of a compound through HPLC. Like you can purify compound in milligram scale only, but by using flash chromatography, we can purify a sample from milligram to in the gram scale, that up to 100 gram. So in our machine, we can purify 100 gram of sample in just one go. But by using HPLC, we cannot purify more than a few milligrams of a sample. So that is the advantage of this flash chromatography. That's why it is most commonly used technique in pharma industry, in the food industry, in the medicinal chemistry lab, in all the CROs which are doing the drug formulation, which are making the drug molecules. It has so many advantages. So it reduce the time of purification. You can have the best purification in a very small time, right? And also the cartridges or the column which we are using in the flash chromatography, they can be used again and again for a long time. So this is from my side about flash chromatography and also the chromatographic technique, especially the column chromatography. So thank you so much for listening and for your patience. Thank you.
Yeah, thanks, Dr. Abid. There is a query from Zohari, who is from University of Bengkulu. He wants to know that if the compound is not compatible with the silica gel, if the analyte is not compatible with the silica gel,
Yes.
then how would you do the chromatography?
That's what I said, that it is not like we have just one silica gel which is available for the column chromatography. So we have a wide range of silica gel. If it is not compatible with the silica gel, then we can go for alumina. Alumina is there for the purification also, right? And also we should look at the nature of the sample, whether it is an acidic molecule or it's a basic molecule. So if we have an idea about the molecule, then it will be very easy to decide which adsorbent we have to use, what solvent system we have to use, and what percentage of solvent we have to use.
Yeah, that is correct. That is true. Sir, I also have a query. Is there no way to separate the enantiomers?
No, it's there. It's there. But I said that by using column chromatography and flash chromatography, we cannot do it. Even also with the HPLC, also we cannot do purification of enantiomers. Okay. But we have another machine, that is chiral HPLC. So chiral HPLC machine it's very expensive. It costs around 1 crore. So I remember when I was working in IIT Kanpur with Professor Faiz Ahmad Khan as a postdoc fellow. So he purchased that machine from Japan, and at that time he got this machine in 1 crore. So actually he was using this machine only for the purification of enantiomers.
All right.
Because he was working on asymmetric synthesis. So when he got a final compound, it was not a pure compound, but it was a mixture of enantiomers. So he was using this machine for purification of enantiomers.
All right. All right. So thank you. Yeah. Any other query for Dr. Abid? There's a query from Anand Selvi, who is our PhD student. He wants to know that can flash chromatography be used for purification of recombinant peptides?
For recombinant peptides.
Peptides, proteins, yeah, for recombinant proteins.
For protein purification, actually we have the FPLC, the flash liquid protein chromatographic machine. It is there in our building also. It's with Dr. Imtiaz. So they are using that machine for doing this protein purification. So protein purification, yeah. So for protein purification, there is another machine. It is not the flash chromatographic machine.
All right. All right.
Yeah.
So any other query for Dr. Abid from our panelists or from students?
Dr. Abid, thank you very much for wonderful presentation. Actually, I enjoyed your talk, and it was just recall of our, MSc time. You explained so well today.
Thank you so much.
One thing I wanted to know that are you medicinal chemist?
I am medicinal chemist, yes, ma'am.
Okay.
So I have two postdocs done in medicinal chemistry, one from Paris, another one from USA. So my lab is established on development of biologically active molecules, and we have the facility for biological activity also. So for antimicrobial, we do ourselves. For anti-malarial, I have a project with a special center for molecular medicine in JNU, Professor Shelja Singh. So she is, a malaria scientist. So she's taking care of the malarial part, the biology part, and I'm doing the medicinal chemistry.
Do you have any, you special focus on some molecules, or you are open to any of the heterocycles?
No, we are working on biologically active molecules, the scaffolds which can give a potential biological molecule. Yes.
Okay, you are open to any of the
Yes, ma'am.
heterocycle.
Yes, ma'am.
I will talk to you later on this meeting.
My pleasure, ma'am. Please, ma'am.
I'm also a medicinal chemist, and I have few students here. So I'll talk to you regarding that.
Sure, ma'am. Sure. Thank you so much, ma'am.
And I thanks Dr. Monica for making you available for this meeting.
So much,
and he put lots of efforts in this.
Yes, I know. Yeah.
Yeah.
So, thanks, Dr. Monica. Yes. Yeah.
Yeah, Dr. Abid, turns out that your lecture is it's liked by a lot of people. So again, Zohri wants to know that how do we know that the compound we have isolated is pure enough? What is an indicator of the purity of the compound? Well,
before doing any spectral analysis.
Sorry.
No. What he want to ask, actually, he want to confirm the purity of the sample after purification, right?
Yes, sir. Yes, sir.
So, see, if you want to, let's say we don't have any facility for, for mass or LC chromatography, right? Then what we should do? Or any purity analysis we cannot do. Then in that case, what we can do, we can run a TLC in different solvents, right? In mixture of different solvents. So if in every solvent system, if your sample is coming as a single spot, it is not turning into 2 or 3 spots, which confirms again that your sample is 100% pure. If you want to be very sure that your sample is 100% pure, you just submit for LCMS. So LCMS will give you 2 important data. One is the purity of the sample, and the second is the mass of the sample.
Exactly. Yeah. One can also use a spectroscopy to
See, if you want to go for spectroscopy, then you have to first go for the UV. It will give you the idea about the transitions, different electronic transitions which are taking place in the molecule, and do you have that lone pair of electrons or non-bonding electrons or the pi electrons. And the best part is you just go for the FTIR so that you can have an idea about the functional groups in the molecule. So if you know functional groups in the molecule and you are expecting the same functional groups in the molecule, it is just the the indication. but you will be sure only after confirmation through proton NMR and 13C NMR.
That is true. That is true. So I think there are no more queries and we can proceed for the demonstration.
So just give me 2-3 minutes. I'm just going to the lab, and then the person is there from the company and they will explain very nicely. I hope it will be very beneficial to the students, because if they are planning to go for higher research, whether it is biochemical research or a chemical research, but this technique, they are very, very useful nowadays. And I hope they will be benefited a lot.
Yes.
So
Sir.
thank you so much again to all of you for giving me this opportunity, and thank you so much, sir.
Thank you, sir. Thank you.
Thank you. So I'm just leaving and I'm again joined from the lab.
Yes, sir.
Okay, sir. Thank you.
Yes, sir. We can see you in the lab now. Sir, you're not audible. Can you please unmute yourself?
Hello?
Yes, sir.
Am I audible now?
Yes, sir.
Okay. So with me, I have a person from Teledyne, Darvesh. He's application scientist. So he's going to explain the, the working of this flash chromatography.
All right.
Right. So is it visible to all of you? The machine. Is the machine is clear to all of you? You can see this?
Yes, sir. Sir, can you take the camera a little bit closer to the screen?
Okay.
Yeah, now it's much better.
Okay. So now I'm handing over this to Mr. Darvesh. He will explain everything.
All right, sir.
Fine. This is CombiFlash next gen system.
Okay.
This is the main screen CombiFlash. Okay.
All right.
Okay. They have two solvent line. This is 1 and 2. One is non-polar solvent. You can see it. This is non-polar solvent and this is polar solvent.
All right.
Like hexane and ethyl state. Okay. This is rack. There are two racks. This is fraction R. Okay. Or this is main screen.
All right.
Main screen, file, method, tools, and help. Okay, fine. Files is your old data. They have saved it for PDF format. This like. Okay. Now start up how to use it. First of all, you can priming the system. Auto prime is for system washing. They can prime A and B for washing the system.
All right.
Okay.
Washing the columns, I believe.
Not the column, like a system washing. Last run is if you are a strong solvent in tubing, they can wash it from through auto prime. Okay.
All right.
First prime strong solvent like B, pump start, then suck its solvent B and wash it. After then pump A. Start. Auto prime is done. Then main system is running. Okay. Now start how to run your column. First you select your column. This is column. This is silk. In column is plastic and in field is silica. Okay. This is 12-gram column. You can see it.
All right.
Okay. Then put it here. And this is normal column. It fill it silica on gel. Silica gel mass size is 100 to 100 ms. Okay. Then you start your method. How to create your method? Your TLC is running 30%. You set a graph. This graph is showing. This is a graph value. In bottom, they are runtime. You select your according your run, according your sample. This is runtime, and this is percentage of B, like strong solvent percentage, 0 to 100. If your TLC is running 30%, you select your graph in 30%. Okay. They can start 100% hexane and they go slightly to 30% in 10 minutes. Okay.
So
This
we are using a gradient, I believe, right?
Yes, you can put your gradient any type, isogradient, gradient, your stepwise gradient. You can put any type of gradient in this. They can select your according your percentage. Okay, fine. I set your 30%. Then gradient is ready for your sample. Then you select your solvent. Which type of solvent use? Hexane and ethyl acetate. I run hexane and ethyl acetate. Ethyl acetate maximum percentage is 30 and go slightly point wise. Okay.
So Mr. Darvesh, can you again tell about the gradient, that how would it change? How would the gradient change?
They can gradient go 100%, start is 100% hexane.
Okay.
They point wise decreases 0.99, 0.98.
Okay.
They reach in 10 minutes 30%.
All right.
Hexane is decreases, ethyl acetate is increases point wise.
All right. All right.
Okay. I can show here how can it work. Okay.
All right.
Gradient is set. You added your sample name. Any. Your run is okay. And start. Sample loading. Sample loading is equilibration, non-equilibration. Equilibration is washing your column. The column is dry. How it is wet? This is equilibration. Okay. Then you select your rack. This type of your rack use. Left rack 60 into 150. This is rack. Okay.
All right.
You can put your rack name and then start test tube number which you want. Fine.
Yes.
And okay. The start machine is start the equilibration. Equilibration that time the solvent is come here and put. They can wash this column.
Okay.
It take total volume is 44 ml for washing the column. In time between, you can ready your sample. This is a liquid loading sample. I put 0.5 ml liquid in direct in column. After the washing, I can forward. The message is here. Put some. Inject your sample. Okay. Then you can remove this tube and put your sample directly. Okay, your sample is go there in column and then put. Okay. Here you can see the percentage of B is point wise increases. Okay.
Yeah.
Hexane is decreasing and ethyl acetate percentages increases.
All right. So from non-polar, we are going to a polar solvent. Am I right?
Yes, you are right. non-polar started is 100% and a polar solvent started is 0.5. So then hexane is started 100% and they reach ethyl state 0.5. You can changes any changes in during run. You want to increase your percentage, then only click here point and increase your percentage. If you want to hold this gradient, isogating hold. Here you can see not increase percentage of B. This is isogating hold. If your compound is come, you can hold their gradients. If you want to remove it, remove it. So here, if you can changes, any changes is possible during run. Okay.
All right. Yeah.
Here you can see that this is your graph. If your compound is come, if peak is come, you can see that your collection is starting in test tube.
Okay.
If compound is come, they select the test tube. Okay. Here mention your test tube number. Everything is here. You can see this memory. This is 254 lambda max, 280 and all valent. Here is 3 types of detection. 254, 280 and all valent. All valent scan 200 to 400 nanometer all wavelengths. If you select all wavelength, they scan 200 to 400 nanometer. Everything scan it this range.
So there is an inbuilt detector in the machine that
Yes,
that can,
yes, yes. The inbuilt PDF detector is machine.
Okay.
Okay. हाँ मैंने सब
Hello.
Yes, sir.
So it's all done from my side. So
All right. All right. Thank you. So I think we have had a wonderful session with Dr. Muhammad Abid and Mr. Darwish. And may I now request Head of the Department, Chemistry, Biochemistry and Forensic Science, Professor Seema Pathak, to deliver the vote of thanks. Over to Madam.
Thank you, Dr. Anurag. So here I am. I'm Professor Seema Pathak, and I'm very happy to see both of my experts here. They did a wonderful job. Thanks Dr. Sal for this wonderful acceptance, and he is actually ready for many purposes. Whenever I get in touch with Monica and I tell her to communicate to Dr. Sal, he immediately responded. You may not be knowing, Dr. Saul, that I and Monica often talk about you, and we used to put how we can utilize our MOU for further. And for Dr. Muhammad Abid, actually, we met you first time, but I hope that you will keep on coming because I found you are a very good teacher.
sure, ma'am, sure.
Dr.
Thank
Sal
you
is
so much, ma'am.
also
Thank you.
explained very well, but because of some language barrier, maybe it is not so comfortable for us. And but I thank him for his response, quick response every time. And I hope that we'll do this workshop again next year. And with more, enthusiasm and more novelty and more good things for our students. I thanks Dr. First, I will start from the person who is organizing this, Dr. Monica Watts, for being very instrumental for doing all those things. And I thank my colleagues, Dr. Anurag, Dr. Bhunesh, my team, Dr. Bumrah, everyone for putting heart and soul and making this event a very huge success. I will thank my, here our Honorable Vice Chancellor Sir and Pro Vice Chancellor Madam, Amity University Haryana, for making us, for pushing us for this type of events and doing wonders for our students and putting all efforts in this COVID time. Also, I thanks my Chancellor, my Director, Professor A.K. Yadav, for being always there whenever we require for organizing this type of events. And to, of course, to my students, actually students, we are there only if you are here. So we love you all, and you actually, I think, heard everything very patiently, and I will tell you that you are going to be evaluated tomorrow for these 2 sessions. So read very carefully whatever sir has told you. And with this, I thank you all for being here, and hope to meet soon again. So because time flies and we'll never realize that when 1 year has come to end. Thank you, everyone.
Thank you, ma'am. Thank you, Anurag sir. May I request the panelists to just open their cameras so that we can have one more photograph, because this time, this occasion will come after 1 year only. So I want to capture it.
Yeah, everyone, Yadu sir also to open his camera. Bumrah and to Bhunesh. I think Dr. Anurag, we can call Professor Yadav, maybe if he's,
Yes,
for opening his camera.
Yes, ma'am.
That we can have photograph.
Yes, ma'am.
Actually, we have to make an extensive report for this type of events. So we have been told to take now geotagged photographs. Dr. Monica is taking so that, everything is in place. So that's why we require all these documentations. Otherwise, scientists never bother for pictures and photos. So thanks for being with us.
He'll be here in a minute. Yeah.
Okay.
Yes, ma'am.
Dr. Bhunesh, Dr. Bumrah se bhi keh dijiye to open his camera. Dr. Deepti is not there, Dr. Monica?
Ma'am, she was here only. I think she must have lost her connectivity. I'm just calling her back.
So, Dr. Yudha, how's the weather in Indonesia? Is it as cold as
Yes.
out here?
Still hot.
Okay.
What is the situation of COVID there, Dr. Yudha? How is COVID in Indonesia?
Yeah, that's, I think, getting better now. The cases only around below of 1,000 cases.
Okay.
So
his third wave is also there.
Pardon me?
Third wave is also there in your place.
Yeah.
You mean to say the corona cases, are they coming back?
He's saying it's still better, improving.
Ma'am, Dr. Bumrah is having connectivity issue, so unable to open the camera.
So let's her join, then we'll have a pic. Dr. Monica, you take, she's taking, I requested her to take geotagged photographs.
Yes, ma'am. We are taking
geotagged camera.
So, sir, is this your lab, Dr. Abid? Is this your? Okay.
Dr. Abid, you did your PhD from which place?
From Jamia Millia Islamia itself. Department of Chemistry. Yes, ma'am.
So he was on top of us.
Yeah.
Yes. Yeah.
Now you are on top.
First floor.
Yes.
Okay, in your this Jamia.
Yes, ma'am.
Dr. Dipti. Sir, I think sir has logged in with via
Sir has
two
come.
devices.
Sir has joined.
Yeah. Dr. Monica, please take pic. Sir, we are done with the all this one proceedings, and we are taking a picture.
Okay, thank you. Thank you so much.
Yeah.
Everything went on perfectly fine.
Tomorrow there is a session again. I mean, that is our internal, this one.
Okay, that's great. I'm so glad
Thank you, sir.
everything went off so well.
Monica, you took photograph? Dr. Monica?
Ma'am, 1-2 more because the location is varying every second. Just one more. Ma'am, I want to state one thing that Abid sir has a vacancy at his lab. If some student who can do 6 months project over his this lab, he will be allowing him to do that work. So his work will be completely on medicinal. So we can.
You told me earlier also.
Yes,
you told me.
Yes. Yes.
I remember.
All right.
Yeah.
So are we through with the picture, Monica?
Monica, is it done?
Yes, ma'am. Yes, ma'am. Just a second. One more, ma'am. Just a second. I'll just mute myself. Ma'am, done. Thank you, ma'am. Thank you, sir.
Thank
you.
Abid,
Thank you.
sir.
Thanks to all.
Thank you, Dr. Yodha, Dr. Abid, and
Thank you, sir. Thank you so much.
all the teams, all the organizing members of the CBFS team.
Thank you so much.
So we meet tomorrow on the second day of workshop at 10 a.m. Indian Standard Time. And thanks everybody for being part of this workshop and making it successful in terms of attendance and knowledge exchange. Have a nice day.
Thank you.